So let's talk about some paired functions that are defined as cofunctions. Sine and cosine are a pair of functions that are cofunctions. Tangent, cotangent, and secant and cosecant. Now, it turns out that cofunctions of complementary angles happen to be equal. And here are a couple examples of problems that deal with this concept. We've got the sine of 38 subtracted by the cosine of 52 without a calculator wouldn't very well be possible, but we know that 38 and 52 are complementary. Sine and cosine are cofunctions, therefore those two quantities are equal. Anytime you subtract something from itself, you get 0. Likewise over here, tangent of 50, cotangent of 40 couldn't be done without a calculator. 50 and 40 are complementary. Tangent, cotangent, cofunctions, therefore they're equal. Anything over itself, 1.
Next terminology, reference angles. So we're going to be given a non-quadrantal angle, which means this angle does not lie on an axis. All right, the reference angle is defined as the angle distance of the terminal ray to the nearest horizontal axis. Now, if you don't understand that, let's take a look at a couple examples. All right, so I have 200 degrees and I'm looking for a reference angle. We want to know where 200 degrees is. It's roughly in the third quadrant if I were to rotate counterclockwise. Now, by definition, this reference angle is defined as the angle distance to the nearest horizontal axis. Well, here's the nearest horizontal axis, and I want to know how far away from that I am. I know that if I rotate half a circle, I'm at 180 degrees. We ended up with a 200-degree angle, so the reference angle for this case, I have 20 more degrees to get to 200, therefore 20 more degrees to get back to 180. Reference is 20 degrees. In the case of a 92-degree angle, 92 degrees puts me somewhere up here, and I need to know how far I am to the nearest x-axis or horizontal axis. This is my closest horizontal. This is not my closest because it's over 90 degrees. So, how far am I away? Well, I've gone 2 over here and it's 90 degrees all the way down. So I'm at 88 degrees is my reference angle. Let's go to the next example. We're going to find reference angles for all the following. So we've got some more positives and negatives. 345 is probably the easiest one on this page. So if I look at where is 345, I'm somewhere in this fourth quadrant. I know I'm at 360 degrees if I go all the way around. So how far away if this is 345? Well, pretty easy. 15 degrees away. That's my reference angle. These next examples are a little bit different because they're not positive, except for the 781, except 781 is more than one time around. So we need to find out where that is. So 781, if you think about it, is more than 2 times around, because if I know one time around is 360, second time around is 270, or 720, sorry. 781 is going to end up 1 time, 2 times, and a little bit more. So here's 781 degrees. That's the terminal ray. So really what I'm asking is how far away is 81 from 20? This angle then has to be 61 degrees, and that's my reference. So now we're going to look at negative 138 degrees. I'm rotating in a clockwise fashion. To this first axis is 90 degrees, to the second is 180. So we are somewhere in the third quadrant. I need to know how many more degrees it takes me to get to the nearest horizontal axis. All right, well, if I'm at 138 here and I need to go to 180, that puts me at 42 degrees. Notice the reference angle is always a positive measurement. It's how far away are you. Lastly, 300 degrees of the negative type. If this is 360, both positive and negative, and this is 270 going in the negative direction, I'm somewhere over here. That's my angle of negative 300. We can see that I have 60 more degrees to get to 360. So that is going to be my reference angle.
Now, in order to keep going, we got to talk a little bit about special triangles because those are going to help us out quite a bit. 30, 60, 90s and 45, 45, 90s that we had in geometry are going to come back once again. All right, some of you know how to calculate these in many different ways, and your teachers have given you certain ways of memorizing which side is which. These may be one of the two up here. I prefer the following. In a 30, 60, 90, I know the short side is half the hypotenuse, and I know the long side is the short side root 3. And then in the 45, 45, I know the hypotenuse is equal to the side root 2, which is kind of expressed right here. Now, from here, we're going to jump to something known as the unit circle. Unit circle is a circle with a radius of 1. And like anything else, if we want to know where a specific point is on that circle, some xy, we could find that by using this right triangle constructed here and say, well, that's just the horizontal distance squared plus the vertical distance squared is equal to the radius squared. But in this case, our radius is going to be 1. So if we wanted to find any of these points, we could just go ahead and use Pythagorean theorem to do that. And we're going to go right ahead and grind some of this out. Now, what I have here is 3 different triangles for 3 special triangles, actually. This is going to be one with a 60-degree angle, a 45-degree angle, and a 30-degree angle. And in each of these, my radius is going to be 1. And rather than using Pythagorean theorem, I'm going to use those special triangle concepts. Now, I know this is a 30, 60, 90. My short side is half the hypotenuse. So my short side, in this case, is opposite the 30-degree angle. So this horizontal distance is a half. Long side equals the short side root 3, so this vertical distance is root 3 over 2. Therefore, I know x and y coordinates are a half and root 3 over 2 for a 60-degree angle. Likewise, I know over in this triangle where I have a 30-degree angle here, the short side is half the hypotenuse, and the long side is the short side root 3. So my x and y here are root 3 over 2 and a half. In this case, we have a 45, 45, 90, and as we stated earlier, I know that the side root 2 is equal to the hypotenuse, so 1 equals the side times root 2. I divide both sides by root 2, and I say the side equals 1 over root 2. By rationalizing, I get root 2 over 2. So each of these sides are the same since it's isosceles and right. So this is root 2 over 2. This is root 2 over 2, thus giving me x and y coordinates that are equal root 2 over 2 and root 2 over 2. Alright, so now that I've established 3 points for some special triangles, let's put these all on the same circle. And if I know that for a 30-degree angle, which is also pi over 6 in radian measure, I have coordinates of root 3 over 2 and a half. For a 45-degree angle, or pi over 4 in radians, I know I have x and y coordinates of root 2 over 2 and root 2 over 2. And for a 60-degree angle, which we also know is pi over 3, we get a half, and root 3 over 2. Now, here's the interesting thing about circles. They're symmetric over 2 axes. So what I know is that I can fold each of these points over into an adjacent quadrant and have the same x and y distances away. So you'll notice, if I flip this point over, I have root 3 over 2 and a half again, except since I'm in the second quadrant, my root 3 over 2 is negative. I have root 2 over 2 and root 2 over 2 again, except my x is negative. And I have a half and root 3 over 2 again, but the half is negative. And also, we will be the same relative angle measure away from the horizontal axis. So in this case, I'm 30 degrees away from 180. That puts me at 150. And I'm pi over 6 away from 1 pi, which is 5 pi over 6. 45 degrees away from 180, which is 135. And I'm pi over 4 away from pi, which is 3 pi over 4. I'm 60 degrees away, which puts me at 120. And I'm pi over 3 away from pi, which puts me at 2 pi over 3. Now, at our exact quadrant measures, we've talked about this a little bit before. This is 90 degrees, pi over 2. And if this is a unit circle, I have 0 as my x-coordinate and 1 is my y-coordinate. Likewise here, 1, 0, negative 1, 0, 0, negative 1. And then I can flip all these points down, get their relative distances away in terms of x's and y's, and their relative angles. And then complete a unit circle for all special triangles. And in fact, that's what this picture shows. Now, you're going to have to know this triangle in and out to be successful in the next week or so. So I suggest you copy this down verbatim, know all the relative degree measures, radian measures for each angle, and the x's and y's associated with them. But once again, all you really have to do is develop this first quadrant right here, and then you can just use symmetry to gather all the rest of your information. So the next thing we're going to do is we're going to find some sine, cosine, tangent values or trigonometric function values for points on this unit circle. Now, first thing we'll do is we'll find the cosine of negative 90 degrees. What I suggest you do when you do these problems is you answer 3 questions. Where are you? What are the x and y points? And which ones do you need? So let's do this. We need to know where negative 90 degrees is, and I'll just sketch out a little quadrant. Negative 90, we're doing a clockwise rotation, so that's down here. And I know that the coordinate points here are 0 and negative 1. And it's asking for a cosine value. Now, if you think about this, let's go to the unit circle again real quick. If I want a value of an angle in general, and I know that this is 1, and I'm looking for a cosine value, and I know the cosine value is the adjacent over the hypotenuse, but my hypotenuse in all these cases is equal to 1, then I'm just looking for the adjacent side, where in this case that adjacent side is always going to be x. So for a unit circle, the cosine of some angle theta is always going to equal x. The sine of some unit theta is always going to equal y. And the tangent, some angle, is always going to equal y over x. This is for the unit circle only, not for those right triangles that we were using before. So if I want the cosine of negative 90 degrees, I'm looking for the x value. My x value is 0. And there's my answer. When I'm talking 210 degrees, let's find out where we are. 210 puts me right here. And what I know about 210, which is very important, is it's 30 degrees away from the horizontal axis. So it's going to have the same x and y coordinates as 30 degrees. My x and y coordinates for 30 degrees are root 3 over 2 and a half. But since I'm in the third quadrant, they're both negative. And I'm asked for the sine value. So when I'm talking about a sine value, I want the y value. Therefore, the sine of 210 degrees is just negative half. So there's how you go through that, find out where you are, what are your points, and which points do you need. Now let's look at these two. We need to know where the cosine of 855 is. Probably the easiest way to do this is take and say, well, how many times would I go around a circle to get to 855? Well, I know that's over 2 times around a circle, so if I take 855 and subtract 720, I end up with 135. So where that puts me is it puts me over here after going 2 times around. So I know that this is like a 135 degree angle. But more importantly, what I should probably know is this measure here, which is 45, because that's going to give me the symmetric flip of the first quadrant that I already know. So I know that my x and y values here are root 2 over 2 and root 2 over 2. But my x value is negative since I'm in my second quadrant. We need a cosine, so we're looking for my x value. My x value is negative root 2 over 2, and that's my cosine of 855. Secant of negative 120, again, let's go ahead and find that. I have to go clockwise rotation 120 degrees, so that puts me somewhere around here. Again, I'm more concerned with the angle closest to my horizontal axis, because that's going to be my symmetry flip, if you will. And it's going to have the same relative x and y's as the first quadrant 60 degree angle. First quadrant 60 degree angle is a half and root 3 over 2. Since I'm in the third quadrant, so we're both negative once again. And I'm looking for the secant value. Secant is the reciprocal of cosine, and cosine is x, so this is just 1 over the x value. In this case, I have 1 over an x value of negative 1/2. Multiplied by the reciprocal here, I end up with negative 2, and that's my secant value. Tangent of negative 300. Here's 300 degrees because I'm going in a clockwise rotation. That puts me 60 degrees away from this horizontal. I know my x and y values at 60 degrees. It's a half and root 3 over 2. I'm looking for a tangent value, which is my y over my x. So in this case, I have root 3 over 2 over a half, which gives me root 3. The cosecant of 390, 360 puts me back here. 390 gives me 30 more degrees up. I know my x and y values are root 3 over 2 and a half. And I need a cosecant, which is 1 over my y. So in this case, my y is a half. So I have 1 over 1/2, which is equal to 2. Hopefully you're seeing how important it is to know which points associate with which angles. Now we're going to jump into the same type of problems but using radians. So 2 pi over 3, we need to find that. 1 pi over 3 is here, 2 pi over 3 is here. My x and y values at 2 pi over 3 and pi over 3 are 60 degrees away. If you need to look at the angles, that's fine in terms of degrees, but I would get to know these radian measures. So I know my x and y values relative to the 60 degree angle or the pi over 3 angle is a half and root 3 over 2. The half being negative in this case. And I'm looking for the cosine value, which is the x value. So again, this is negative half. Sine of negative 11 pi over 6. Clockwise rotation, 12 pi over 6 is 2 pi, so I'm pi over 6 away from that axis, which is kind of like a 30 degree angle. And I know my x and y values are root 3 over 2 and a half. I need my y value because I'm talking about sine. So that's just going to be a half. Tangent of 5 pi over 3. Well, 6 pi over 3 is 2 pi, so I end up somewhere over here, pi over 3 away from 6 pi over 3. I know my x and y values are similar to those of 60 degrees or pi over 3. So that's a half and root 3 over 2. Except in this case, the root 3 over 2 is negative. Tangent's y over x. So if I take my y value of negative root 3 over 2 over a half, multiply by the reciprocal, get negative root 3. And there we go. Secant negative 22 pi over 3. Now, what I do when I get measures way over like 2 pi that I can't really count out in my head is I'll reduce these to a mixed number. So this is like secant of negative 7 and 1/3 pi. Now, the question is, where is 7 and 1/3 pi? Well, let's do this. Here's 0 and here's pi. And then when I come back, I'm at 2 pi. So this is 1 pi, 2 pi, 3, 4, 5, 6. There's 7 pi. And then if I need to go another third, remember I'm going in a clockwise fashion. I'm going to go a third more pi in this direction. So I get to 1, 2, 3, 4, 5, 6, 7 pi, and one more third pi puts me over here, which is pi over 3 away from this axis, or 60 degrees. I know that 60 degrees away from this axis, or pi over 3, has x and y coordinates of a half and root 3 over 2. But the half is negative. And I'm looking for a secant, which is 1 over the x value, which is, in this case, 1 over negative 1/2. So I end up with negative 2. All right, here's another one. 47 pi over 4. Again, I'm going to change that to a mixed number. So this is the cosecant of 11 and 3/4 pi. And I'm going to go through that same argument of how to get there. Here's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pi. And I need to go 3/4 pi from here. 3/4 pi would put me over in this quadrant here, somewhere around pi over 4 away from that horizontal axis there. I know coordinates of pi over 4 are root 2 over 2 and root 2 over 2. However, the y is negative since I'm in my fourth quadrant. And I'm looking for a cosecant. Cosecant is 1 over the y. So I have 1 over negative root 2 over 2 multiplied by the reciprocal, get 2 over root 2, and rationalize. So I end up with negative 2 root 2 over 2, which is negative root 2. That was a lot for today. You've got to get that unit circle down. You've got to understand which points correspond to which angles and start being familiar with radian values. Do your My Math Lab, and we'll talk about this tomorrow.